Cardiovascular physiology, the cardiac cycle. Welcome to today's episode, where we delve into the intricacies of the cardiac cycle, the remarkable sequence of electrical and mechanical events that span from the start of one heartbeat to the beginning of the next. This process is essential for understanding how the heart operates as a rhythmic pump, sustaining life with its continuous flow. Let us begin by exploring the core concept. The heart functions in a rhythmic cycle, filling with blood and then ejecting it, all guided by the coordinated contractions and relaxations of the upper chambers, the atria, and the lower chambers, the ventricles. Each event is precisely timed, aligning with changes in pressure, the opening and closing of valves, and shifts in blood volume within each chamber. In essence, the cardiac cycle is divided into two main parts. The first is systole, which is the period during which the ventricles contract and propel blood out of the heart. The second is diastole, the phase when the ventricles relax and refill with blood. The entire sequence is further divided into 7 distinct phases, each with its own characteristics and significance. It is important to note that blood flow through the heart is always directed from regions of higher pressure to lower pressure, and the function of the heart's valves is completely passive, relying solely on these pressure gradients. Let us walk through the 7 phases of the cardiac cycle, focusing on the left side of the heart for clarity, although the right side mirrors this process at much lower pressures. We begin with ventricular filling, which occurs during diastole. The first phase is atrial contraction. At this moment, the electrical impulse responsible for atrial activity is detected as the P wave on an electrocardiogram. Mechanically, the atria contract, and the pressure within the left atrium slightly exceeds that within the left ventricle. The valve between the atrium and ventricle, known as the mitral valve, remains open, while the valve leading to the aorta stays closed. This contraction gives the ventricles their final kick of blood, contributing roughly 10 to 25% of their volume just before contraction. Typically, this phase is silent, but in certain medical conditions, a fourth heart sound may be heard. The second phase is isovolumetric relaxation. This follows the completion of the heartbeat, marked by the T wave on the electrocardiogram, which indicates ventricular repolarization. Here, the ventricles are relaxed yet remain closed chambers. As the muscle relaxes, pressure within the ventricles falls rapidly, dropping below the pressure in the aorta and soon beneath that in the atrium. All valves are closed during this interval, and the volume within the ventricles does not change. The closure of the aortic and pulmonary valves produces the second heart sound, signifying the end of ventricular contraction. Next is rapid ventricular filling, the third phase. This occurs as the pressure in the left ventricle drops below that in the left atrium, prompting the mitral valve to open passively. Blood that has accumulated in the atria swiftly flows into the relaxing ventricles, accounting for the majority of ventricular filling. Sometimes, a third heart sound is audible, particularly in young individuals or those with certain heart conditions, caused by the vibration of blood against the ventricular walls. The fourth phase is slow ventricular filling, also known as diastasis. During this phase, passive blood return continues to fill the ventricles, but at a much slower rate. The pressure in both the atrium and ventricle is nearly equal, and the mitral valve remains open while the aortic valve is closed. This stage shortens considerably when the heart rate increases. We now transition to ventricular ejection, which occurs during systole. The fifth phase is isovolumetric contraction. This phase is initiated by the QRS complex on the electrocardiogram, representing ventricular depolarization. The ventricles contract forcefully, causing the pressure within them to rise sharply, though the volume remains unchanged. Once this pressure exceeds that in the atrium, the mitral valve closes abruptly, and the pressure continues to build until it is just greater than that in the aorta. All valves are closed during this brief moment, and the closure of the mitral and tricuspid valves creates the first heart sound, heralding the onset of ventricular contraction. The sixth phase is rapid ejection. Now, as the pressure in the left ventricle surpasses that in the aorta, the aortic valve opens, and blood is propelled swiftly out of the ventricle into the aorta. This phase is responsible for the majority of blood ejected with each heartbeat, and the pressure within the aorta rises to its peak. The seventh and final phase is reduced ejection. As the process of ventricular repolarization begins, contraction of the ventricle diminishes and the rate of ejection slows. The pressure within the ventricle falls slightly below that in the aorta, but blood continues to move forward due to its momentum. The aortic valve gradually begins to close, and only a small amount of blood is expelled during this phase. The volume remaining in the ventricle at the end of this stage is known as the end systolic volume. Once these 7 phases are completed, the cycle repeats itself, beginning anew with atrial contraction. To summarize, there are several key volumes and heart sounds that clinicians use to assess cardiac function. The end diastolic volume is the amount of blood present in the ventricle just before contraction, often referred to as the preload. The end systolic volume is the blood remaining after ejection. Stroke volume is calculated by subtracting the end systolic volume from the end diastolic volume, representing the quantity of blood ejected with each beat. The ejection fraction, a crucial clinical measure, is the proportion of end diastolic volume that is ejected during each cycle. As for heart sounds, the first sound marks the closure of the mitral and tricuspid valves at the beginning of ventricular contraction. The second sound denotes closure of the aortic and pulmonary valves, marking the onset of ventricular relaxation. The third sound may be heard during rapid ventricular filling, and while normal in youth, it can indicate heart failure in adults. The fourth sound is always abnormal, signifying atrial contraction against a stiff or non-compliant ventricle. Finally, all these events and relationships are beautifully illustrated in the classic Wigger's diagram. This powerful visual tool brings together the electrical activity of the heart, pressure changes in the various chambers and vessels, the timing of heart sounds, and the dynamics of ventricular volume. The diagram provides a complete and elegant picture of how the heart functions as a highly coordinated and efficient pump. Thank you for joining us for this comprehensive exploration of the cardiac cycle. Stay tuned for more deep dives into the wonders of human physiology. If you enjoy our content, please like, share and hit the subscribe button. It's the Everything Surgery Podcast. Dissect the extraordinary.